So let's today discuss basis and dimension. Okay. So we are going to start with the definition. The definition is this is the definition of the linear dependence. So let's start with let V be a vector space over the field F, and let us consider a subset of subset S of the vector space V is said to be linearly dependent if there exist distinct vectors u1 vector, u2 vector, and un vector in S, and scalars c1, c2, cn are not all of which are 0, such that c1 u1 plus c2 u2 plus cn un is equals to 0. So this is the definition of the linear dependence. So we are considering a set S of the original vector space V, and in this set S, I am considering these distinct vectors u1, u2, un, and I am considering also c1, c2, cn. These are the scalars. Then if c1 times u1 plus c2 times u2 plus dot dot cn times un vector is equals to 0 vector, then we say that this set S is linearly dependent. Okay, so a set which is not linearly dependent is called linearly independent set. So a set which is not linearly dependent is called linearly independent. So there is these things. So we don't say when S is a finite set. So S consists of finitely many vectors. Then we don't say S is a linearly independent or dependent set. Rather, we just say that the set is linearly dependent or independent. Okay. So there are some, yeah. Is there any question? What?
I was thinking where is
Okay.
what set is.
Yeah. So some consequences of these definitions are, the first one is, if I consider a set which contains linearly dependent set, so is that set also, so I'm considering a set S, then I'm considering another set, let's say U, and if uh, S, if U contains S, that means S belong to, S is a subset of U. Is that set also linearly dependent?
Yes.
Okay, right. So this set is also linearly dependent. So that means the first consequence is any set which contains a linearly dependent set is also linearly dependent. So the next consequence is if I consider a subset of the linearly independent set, is that set also linearly independent? So I'm considering, so let us consider first that this set S is linearly independent. Okay. So if I take a subset of this set S and I consider S prime is a subset of this set S, then is S prime also linearly independent? Is it? Why is that?
Another condition has to validate that we condition the satisfied number of them.
So, so what is the definition of linear independence or dependence?
Yeah.
So this has to satisfy, right? When not f is c1, c2, cn equal to 0. Okay. Then that means what is the definition of linear independence? So that means what is the condition on in this summation? What will be the condition?
Not equal to 0.
No. So if I set this summation equal to 0, then what will be the condition for linear independence?
C1, C2, all has to be 0.
Yeah, C1, C2, all has to be 0. So let us consider for S, let's U1, U2, Un. There are n many vectors in this set S. So this is the set S. So since this set S is linearly independent, that means if I take the summation C1 U1 vector plus C2 U2 vector plus Cn Un vector equal to 0, then 0 vector, then all this C1 equal to C2 equal to Cn equal to 0, right? This is the definition of the linear independence. Now, if I take a subset of this set, so the first one is what? What is the subset of this set? Yeah, you can take any number of vectors from it, right? So then it will be like if I take u1 comma u2 vector dot dot um vector where m is less than n, and if I consider this to be the set S prime, then is that set also linearly independent?
Yeah, so we said that বলা ছিল যে সবাই zero হতে পারে। Yes.
Which set?
Yes, sir, সবাই zero হতে পারে।
So no, I'm considering a set S where these vectors are non-zero vectors u1, u2, un.
C equal to
See, yeah, the scalar has to be zero, right, for the linear dependence. Then if I take the subset S prime, then this has to be also a linearly independent set, because if I take the linear combination from this set, like C1 U1 vector plus C2 U2 vector plus M um vector, and if I set the assumption is equals to 0 vector, then all these C1 prime equals to C2 prime equals to Cm prime has to be 0, right?
why?
Yeah. Yes, sir.
Why is it the case that these scalars are identically zero?
Yeah, because since this u1, u2, and um, these are the linearly independent vectors, and if I set this summation is equals to 0, then the scalar has to be 0. Otherwise, the summation will not be 0, right?
So, but I'm supposed to show that this is a linearly independent set.
Yeah. So
But
I'll prove that theorem in a few minutes.
yeah, but what are our goals? What is our goal? Our goal is to show that any subset of a linearly independent set
Yeah.
is also linearly independent.
Yes.
That is what we want to show.
Yeah.
So we started with that set u1, u2 all the way up to un.
Yeah.
That is a linearly independent set. And that is why we set an arbitrary linear combination to the zero vector, and that shows that C1 equal to C2 equal to Cn is equal to 0.
Right.
Now we are taking a subset of that set,
Right.
which you have written down as S prime.
Right.
And now I need to show that this is a linearly independent set. Now you started with an arbitrary linear combination. This does not have to be the same linear combination.
Yes,
C1
right.
prime, C2 prime, U2, right? Is
Yeah.
equal to the 0 vector. Now you need to show that C1 prime is equal to C2 prime is equal to Cn prime is equal to 0.
Yeah, right.
So how do you show that?
Sir, I will prove that theorem in a few moments.
Yeah.
So I'm just introducing the idea, then I'll prove that theorem in a few moments.
Yeah. So we will not prove it. It
Yeah.
requires a proof, right?
Yeah, right. Yeah.
Yes, and you are stating that S is a linear dependent set or independent set?
Dependency.
So for dependent set, you have to take a bigger set that contains the linear independence, and that is going to be linear independent as well.
Yeah.
Because the smaller set is linear independent. Therefore, the bigger set which contains the smaller set has to be linearly dependent as well.
Yeah.
But it's the other way around for the linearly independent instrument. Right? Now that requires a proof, Jim.
Yeah. Sir. Okay. So So another consequence is any set which contains.
So this part is untrue.
Yeah.
You are going to prove it.
Yeah. It requires proof. Any set which contains the zero vector is that set a linearly dependent set or independent set? Yeah. Why is that? So what is the definition of linear dependence and independence? Again.
And then I can have C1s and C2s equal to 0. To make any non-zero vector 0, we need to add a zero stable line. So we need C1 to Cn and all of them has to be 0.
No. So the definition of linear dependence is C1 U1 vector plus C2 U2 vector plus Cn Un vector is equals to 0 vector. Now, it doesn't mean I have to take all the elements from the set S and I have to take the assumption, right? Even if I consider C1 U1 vector is equals to 0 vector, right? So, if any set which contains the 0 vector, that is, let us consider the set as S, and let this consider 0 vector belongs to S. Then this implies that then any number, non-zero number C1 times 0 vector, this is equals to, yeah, because we proved it, right? So that means this shows that any vector that contains the 0 vector is linearly dependent. And yeah, so and another way to show that you can so if u belongs to S, u vector belongs to S, and consider -1 times u vector plus 1 times u vector, this is equals to 0. That means my so that means my C1 is -1 here and C2 is 1 here, right? And this summation is equals to 0 vector. That means this set is linearly dependent. And now for final, a set is of vectors is linearly independent if and only each finite subset of S is linearly independent. I.e. if and only if for any distinct vectors u1 vector, u2 vector, un vector of S, c1 u1 vector plus c2 u2 vector plus cn un vector is equals to 0, where each ci is equals to 0. Okay. So a set S of vectors is linearly independent if and only if each finite subset of S is linearly independent. I.e., if and only if for any distinct vectors at the of S, at the equals to 0.
So this C1 U1 vector plus C2 U2 vector all the way up to Cn UN vector is equal to the 0 vector implies that each Ci is equal to 0, not where is Ci. When you say where is Ci equal to 0, you assume that Ci is not 0. But you want that equal to 0 will imply that each Ci is equal to 0, right?
C equals to 0.
But when you write where,
Yeah.
it means something else.
So it implies that each Ci equals to 0. So so this is actually the main theorem, and this one is the kind of corollary of that theorem.
This is much stronger.
Yeah. Okay, so now let me give you an example of this.
Are you going to prove it?
So I will prove it later. Let F be a field in Fn. Let F be a field in Fn, and let S be the subset.
What do you mean by Fn?
I mean, subspace.
It is also not clear. What do you mean by F be a field in F to B? F to B is a vector space over F. So are you considering that vector space?
Yeah. Let Fn is the vector space
over F.
F. Let S be the subset consisting of the vectors epsilon 1 is equals to 1, 0, 0. This epsilon 2, 0, 1.
I think you can put 0 at the end. That means it's fine.
That. So, and finally, epsilon m, 0. Okay. So, is this set S is a linearly independent set or dependent set? Why is that?
Because for only the scalars,
So how can I write it? So I can write any arbitrary vector epsilon using some numbers, let's say x1 times epsilon 1 plus x2 times epsilon 2 plus xn times epsilon n. Okay. Now, so this is the arbitrary vector. So this is the arbitrary vector, right? And this arbitrary vector can be written in this form. Do you agree? Okay. So then that means is uh, yeah, hence an element x1, x2, xn belongs to fn can be expressed in this linear. Yeah. So which one? No. This is the vector. It belongs to the vector space f to the n.
F to the n is the
Vector
vector space
space.
of all n tuples when each entry is coming from the field F.
Yeah.
Therefore, F to the n.
Yeah.
Suppose R to the n.
And also if zero vector is equals to, if you take the set the linear combination is equals to 0, then x1 epsilon 1 vector plus x2 epsilon 2 vector plus xn epsilon n vector. So what is the zero vector? What do we mean by zero vector belongs to fn? Sorry. What do you mean by zero vector in fn? Yeah. Yeah, but what is that zero vector? So fn, this is the sir already said that this is a yeah n tuples of numbers, right? Then what is zero vector?
N zeros.
Yeah, n zeros. That means zero vector is actually 0 and 0. This is the zero vector, right? Okay, so if I said this linear combination is equals to 0, where each epsilon 1 is this, and this, then is all these scalars like x1, x2, xn, are they all going to be 0?
No.
Yeah? Yes?
Actually, to ones.
Yeah.
So, to 0.
And since these,
You can do even more directly.
yeah,
Multiply x1 with epsilon 1 vector. What do you get?
One into n minus 1 series.
So write
it is like
x1, comma
x1, comma
0,
0
0, 0, 0. Everything 0.
plus
Plus 0
x2,
x. No.
0, x2, sorry, 0 plus 0, 0, xn. Then if I write all this x1, comma x2, xn, and this is equals to the 0 vector, which is 0, 0, 0. Now if you compare, so this is just one. So this is x1 equal to 0, x2 equal to 0, all the way up to xn equal to 0, right? That means this set is linearly independent. So is it possible that a infinite number of set is also linearly independent? Yeah, a set. So I'm considering a set which consists of infinite number of vectors from a vector space. So is it possible that this set also linearly independent?
That depends on the dimension of the space.
No, I just said that, right? I still didn't define what the dimension is.
We can't say.
And why is that? Why?
Because if we take infinite numbers, because we haven't defined how infinite it can be. Because if we take infinite numbers as you said, we may end up finding that two vectors are correlated.
No. So the thing is, so let us consider another example. Let F be a subfield of the complex numbers and let P be the set of polynomials functions over F. So what is this polynomials function? These polynomials functions are functions from the field to the field, right? So this polynomials function F is the functions of F to F.
We define it from set to field.
Now I'm defining it from field to field. Okay. So then f of x can be written as, for an n degree polynomial, this is equals to c naught plus c1x plus cnx to the n. Yeah. And let us consider that if k of x is equals to x to the k, for k equals to 0, 1, 2. Now, if we consider
C1, C0, C1 all the way up to C8 to be the field, right?
yeah, this C1, C2, C, I mean this CIs belongs to the field. Okay. Now, if we consider the set S, which is equals to the set F naught F1 dot 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 F K dot dot dot, is this set linearly independent or dependent?
If equals to f case.
No.
Yes.
So that's why I put a dot there. That means
This is an infinite set.
infinite set.
When fi is defined by
This
fi
is
of x equal to x to the n. Now the question is if this set is linearly independent. Yeah.
and so from this theorem we didn't prove yet
And I'm more concerned with the set that you have written. Do they understand what is the zero vector of that vector space?
Yeah, so I'm going to define it. Okay. So we will use this theorem to prove that. Yeah. Okay. So let us consider. Uh, so if I use that theorem, this one, it says that a set S of vectors is linearly independent if and only if each finite subset of S is linearly independent. So that means I'm considering this infinite set, right? Yes. So if I can able to show that a finite subset of this set is linearly independent, then
The whole set is
independent, right? So now let us consider a subset is prime, which is the subset of that set, and that is f0 if n. Okay. So okay, so now let us take a linear combination of that set. So C0 F0 plus C1 F1 plus Cn F1. So I'm taking a linear combination of that set. Okay. And so what Sar is saying is I have to take can you tell me what is the zero vector of this set, of this polynomial set?
zero vector should be C0 equal to 0 and 0 F0 equal to half.
No. So the polynomials is defined in this way. F to A, where f of x equal to this. So
what are the elements of this vector space? First, identify the elements of this vector space. These are polynomials, right? You can add two polynomials, and you can multiply the polynomial with a scale, and the scalar is coming from f. Okay. So how do you add two polynomials? Just add that, right? Of different degrees. So possibly of different degrees, you can order that.
yeah.
So the resulting degree of the polynomial would be the
Maximum.
one of the greater degree.
So if I consider,
there is another caveat, G.
Yeah.
You are choosing any subset, right?
Yeah.
Why are you choosing a preferred subset F0 to F? It could be like F1, F3, F7, F9.
Yes, sir. But the theorem says that if I
You
can
have to
able
prove that if and only if every subset.
but if any subset of that,
Can you please go back to the theorem?
yeah.
If and only if each finite subset of this, each.
So
it's
if
not just one of them that you have to show. Is that correct? Right. So there is stronger version of it. Yeah, you can always do that. How do you do it? So it was just a comment.
yeah, so okay. So I understand what you're saying. So
But first of all,
yeah.
just clarify the vector space
Yeah.
structure.
So the vector space structure, I think I already defined it in the previous lecture. So
the function space.
yeah. So if I take two polynomials, even if they are different degrees, like f and f prime, then f plus f prime is defined as this is equals to f of x plus f prime of x, right? So what will be the zero, the additive identity of that vector, this vector space?
Zero function.
Yeah. So zero polynomials. So that means I have a zero vector here, and this is equals to,
Zero.
yeah, that means zero. But this zero, is it a vector? Or,
That area for the field.
yeah, this is an element of the field. Now,
For every f in the domain, we should get the zero.
yeah. So
So it maps any x to 0.
yeah. Right. So now let us take this. So I already take this linear combination, this, right? And now if I set it to zero vector, then this will be c0 f0 plus c1 f1 plus cn fn. This is zero vector, right? But this can be written as c0 f0 plus c1 f1 plus cn fn of x vector, sorry, yeah, x is equals to zero vector of x. That means c0 f0 of x plus c1 f1 of x plus cn fn of x is equals to 0. That means this is just simply c0, right? Then c1 x plus cn x to the n, this is equals to 0. But what this equation actually tells us?
This equation says that we have 0 into 1 plus 0 into x0.
No.
So we
So
can say that for any value of x,
x,
it has to be satisfied.
Because-
Is it always possible?
because I choose x arbitrarily, and this arbitrary x, when I act zero vector on that element x, this is equal to 0. And this x is arbitrary, right? But this is a polynomial equation, right? So this polynomial equation, is it possible for every x in the left hand side, this is equal to 0? So there are how many solutions for this polynomial equation? Yeah. So there are n solution for these polynomials, but the construction of the proof, it from the construction of the proof, we can see that this is actually possible for every x. So this is the so this is actually not true, right? Because
for number greater than
yeah, so x1 xn, there are these many solutions for this polynomial equation, but the construction of the proof, I choose x arbitrarily. This x can be any number of x, and I can set any x and this is equal to 0. That means this is only possible if
the scales.
the scalars c0 equals to c1 equal to cn equal to 0. right? Okay. So then what Sir was saying is why I choose this set F0 Fn. What if I choose some other set like C0, sorry, F0, F3,
F100,
F100,
F1000.
F1000. If I choose this set, just consider F10.
You need to prove that this is also linearly independent.
Then we will have 1000 number of solutions. Maybe we will have a lot of zeros in problem. We will have 1000 number of solutions for any, but for any arbitrary f x in f, we have the solution.
Yeah, so if I take the linear combination of this will be C1, sorry, C0 plus C1 x cube plus C2 x10 plus C3 x to the 100 plus C4 x to the 1000. So how many solutions this polynomial equation have? Maximum 1000. Yeah, but this is if I set this equals to 0, that means for arbitrary x this is possible, and this is only possible if these numbers C0, C1, C2, C3, C4, all these numbers has to be 0. Okay?
No, but it is not the thing that I was suggesting. So if you go back to your example,
Yeah.
now the set that you are considering, S prime. Okay. Now somehow I have to prove that. So I have shown that this is a linearly independent subset, right? Now I have to show, I am supposed to show that any subset of S is a linearly independent subset.
Yeah.
So now I have to show that it is sufficient to prove that the subset is linearly independent subset, and that every subset of S is linearly independent follows from this.
Right.
That I have to show. How? Because I can change it arbitrarily and so on. And all other subsets that we consider actually be subsets of S prime for a certain value of n.
Right.
And now, and we already know that if a subset is linearly independent, any subset of that is also linearly independent.
Yeah.
So that proves that any subset of S is linearly independent, and that proves that S is linearly independent. Right? That is the argument precisely.
Yeah.
So from F0 to Fn, it is sufficient to prove that this is linearly independent. But why it is sufficient? Because all other subsets will be a subset of these subset for some value of n.
Right.
And we know that any subset of a linearly independent set is linearly independent. That proves that any subset of S is S, not S prime. S is linearly independent, and that proves that S is linearly independent.
Right.
Right?
Yes. Okay, so okay, so for this theorem, now a set S of vectors is linearly independent if and only if each finite subset of S is linearly independent. So okay, so now if I consider if the set S is linearly independent, So if I consider the set S to be linearly independent, then, and if S is like any arbitrary set, right? So yeah, okay, let me state the theorem again. A set S of vectors is linearly independent dependent if and only if each finite subset of S is linearly independent if and only for any distinct vectors u1, u2 vector, un vector of S c1 u1 plus c2 u2 is equals to 0 implies Ci is equals to 0. Okay. Okay, so let us prove this theorem.
Is the zero vector on the right hand side?
Yes, this is a subset of S is linearly independent. So if this set S is linearly independent, and if S consists of infinitely many vectors, then I can write something like C1 U1 vector this infinite summation equals to 0. This has to be the condition which implies each Ci equals to 0. Right? This is the definition of the independence of the set. Okay. So from this way, now if I
Which direction are you moving?
in the forward direction side, I'm considering S to be a linearly independent set. So then yeah,
If this condition is true, then if we take finite number of views,
yeah,
then it will always be 0.
yeah. That means if I take the finite uh, summation of this, then it is actually 0. So this implies that C1 U1 vector plus C2 U2 vector plus Cn Un vector, this is equals to 0. Now for the reverse direction, we'll have to show that if C1 U1 plus C2 U2 plus Cn Un equal to 0, that means so if C1 U1 vector plus C2 U2 vector plus Cn Un vector, this is equal to 0, then I can add infinitely many vectors with these vectors multiplied by 0, right? Yeah. So I can add C1 U1 vector plus C2 U2 vector plus Cn Un vector plus 0 times Un plus 1 vector plus 0 times Un plus 2 vectors plus infinite summation, and this is also equal to the 0 vector, right? Sir, is it sufficient? I think, yeah, because if I multiply some other number with a vector, then the summation will not be 0. But is it sufficient?
What are you trying to do? You are trying to prove that. So write down what you want.
So I want to prove
Then you will
if
be
C1 U1 vector plus C2 U2 vector plus Cn Un vector, this is equal to 0.
0 vector.
Yeah, 0 vector
For any n.
for n.
So these 0 vector implies C1, C2 all the way up to Cn is equal to 0.
Yeah,
So write down.
for each Ci equal to 0.
No, not for each. So this is equal to 0.
Sorry,
vector
this implies.
Implies each
Ci equal to 0. Then I want to show that
C1 U1
C1 U1 vector
C1 prime.
U1 vector prime. Sir, do I need to consider?
So starting from the U,
Yeah.
you chose the first n vectors.
Yeah.
There.
Right.
Now you write C1 prime U1 vector plus C2 prime U2 vector, not plus C2 prime times C2 vector.
Yeah.
Plus the infinite sum.
Yeah, first, let me specifically remove Cn Un vector prime plus
Cn prime.
Yeah.
Plus the infinite vector, infinite sum
is equal to 0.
Will imply
Implies
that C1 prime
C1 prime
equal to C2 prime equal to Cn prime equal to infinite equal to 0. Right?
Yes.
So whenever one needs to do something, one needs to specifically write what one needs to show.
Right.
Now one has to figure out how the given statement implies that this is the case.
Yeah, so for this part,
For the first name 0, the first C1 to, and we already know that they are zeros. But for the rest,
So now one starts with this, what is given.
yeah.
So this is given, C1 prime U1 vector plus C2 prime U2 vector plus Cn prime U1 vector, not that one.
Yes.
This is also given, the last line. This is also given, right?
Yeah.
One needs to show that all these scalars are identical, right?
Right.
And now tell me one thing, if so if this is given,
So I actually the given part is actually C1 prime
yeah,
U1 plus
right,
C2 prime U2
right, Cn
plus
prime U
Cn prime Un vector equal to
equal
0.
to 0, right?
Now,
Because you can always choose those C1s
Yeah.
as C1 primes. There is no harm. And this will imply that C1 prime is equal to C2 prime equal to Cn prime is equal to 0, right?
Right.
Then you start with n plus 1 term.
right. So if I add another term, C1 prime U1 vector plus C2 prime U2 vector plus Cn prime Un vector plus Cn plus 1 prime Un plus 1 vector, and if I set this to 0, then what will be Cn plus 1 prime?
0.
It has to be 0, right? Otherwise, this is not the 0 vector.
So we can use induction.
Yeah,
We can use induction.
but for infinite,
For n plus 1.
yeah. So I'm taking a series summation. This should be a 0 vector. It is easy to prove for uh, the Euclidean space because infinite list is linearly independent. But for an arbitrary space, how can I show that? Okay, sir, I think I have this. So if this infinite summation if I consider this C1 prime U1 vector plus C2 prime U2 vector equals to 0, C1 C2 1 not equal to 0. This point is infinite summation. Yeah, but let me try some few moments. Okay, so so this is equals to 0. Okay, I think, but sir, for infinite set, there is a subtlety. Yes, it is true. If I, it is definitely, it can be proved by induction, but when we are considering induction, then
You said that it is possible.
I think you were trying to prove it by induction. I think this is the right way.
yeah. So then this is actually true, because if I set this to be zero vector, this is true. Then if I add both sides by c1 prime u1 plus c2 prime u2 vector plus cn prime un plus cn plus 1 prime un vector is equals to 0 vector plus cn plus 1 prime.
So why do you do that?
Sorry, sir.
You don't need to do that. So you set it to with the zero vector.
Yeah.
And that will imply that C1 prime is equal to C2
The first part is actually 0. Then I'm adding 0 vector plus cn plus 1 prime u n plus 1 is equal to 0 vector. Then the left hand side is cn prime plus 1 un plus 1.
because none of these vectors are zero vectors.
Yeah.
Set, right?
Right. That means,
Otherwise, it will be linearly dependent.
yeah. So if this is equal to 0, then cn plus 1 prime is also 0 vector, right?
And since n was arbitrary,
Yeah.
it goes for
So n belongs to the number, natural number.
so since n was arbitrary, it proves that C1 prime equals C2 primes.
All this,
terms
all the
are
up to infinity, all these numbers are 0. Yeah. Right.
zero.
Yeah.
I think you were mainly focused on for non-Euclidean spaces, say for
No,
functional
but when we are choosing the set, so yeah, finite set or even the infinite set, we are labeling each vectors by a sequence of numbers, right? 1, 2, 3. So if when I'm considering the summation, the summation is c0 times, so c1 u1 plus c2 u2 plus c3 u3 plus dot dot cn un plus dot dot
for
infinite.
functional space.
Yeah.
Then we can pick one and
No, not just functional space, even for a for a arbitrary abstract vector space, it's true. Just you have to take a infinite number of element from the vector space, right? Okay, so I'll look into it in a more detail, and if I see some subtlety here, then I'll definitely let you know. And okay, so let me prove another theorem. This will be the last one. Let V be a vector. So to define, okay, so let me define the basis first. definition. Basis and dimension. Let V be a vector space over the field if a basis for V is a linearly independent set of vectors in V which spans the space V. The space V is finite dimensional if it has a basis so finite basis. So the definition of the dimension is the number of elements that consist in the set S which spans the vector space. Okay.
Which is also linearly.
Yeah, which is also independent. Now, so can you tell me what is the basis of standard basis of the Euclidean space? No, for Euclidean space that means I'm considering the R to the N. Yeah, that is exactly this one. Yeah, this one, the standard Euclidean basis. Okay, so let me state it here. Let V be a vector space over F which is spanned by a finite set of vectors U1 vector, U2 vector, UN vector, vector, then any independent set of vectors in V is finite. V is finite and contains no more than m elements. So the theorem states that if I consider this vector space V over the field F, which is spanned by these vectors, then any independent set of vectors in V is finite and contains no more than m elements. Okay. So if you take another independent set from this same vector space V, that vector space will have at most m elements, right?
Eventually, variable are independent of the one.
Yeah. So, so what we can do for the proof is we can prove if the set we can prove so if the set contains n elements and if n is greater than m, then the set is linearly dependent, right? So if we can show this, then that means this theorem is true. Okay, so let us consider so let u, so it is already given that u1 u2 dot dot un is the set of, so this is the set which span the vector space V. Okay, and I'm considering another set v1 v2 dot dot, so m vn, this is the set S prime, and I'm also considering that n is greater than m. Okay, right? Okay, so now
The first set S spans the vector space.
yeah, right, because it is in the theorem. So that's why there is a m and in the below is. So since this this set A spans the vector space V, and all these vectors v1, v2, vn are the elements of the vector space V, then I can write each vi is equals to the linear combination of these vectors. That means vi, vi vector. These are all vectors. Is equals to sum aij uj, where j equals to 1 to m. Okay, so can you tell me why it is possible to write this vector as a linear combination? Because I proved the theorem. Yeah. And what was the theorem? That
Linear span of a subset is vector space.
no.
Linear span of a subset is
The vector space spanned by the set S contains all the linear combination of that set, right? All possible linear combination. Okay.
We also proved that that is also the smallest.
Yeah. So vi is equals to j equals to 1 to m aij uj, where each aij are the elements of the field. Right. So now what I can do is I can take the summation in the left hand side, like x1 v1 plus x2 v2 plus xn vn vector is equals to summation of I equals to 1 to n xi vi vector, right? And this is equal to I equals to 1 to n xi summation j equals to 1 to m aij v sorry, uj vector, right? Okay, so I can rearrange the summation and write it like j equals to 1 to m and I equals to 1 to n aij xi uj. Sir, I think I made a mistake, sir. I should have started with this. This is j I yeah, yeah. No, there will be a problem if I don't do this. So then this is just j. This is just j. J equals to 1 to n. And this is I. J. I j. And this is yeah. This is ui.
It's J.
J.
UI vector.
Yeah. Okay. So now this is if I'm considering a matrix of size m cross n.
You have to
This,
indices are correct, not correct.
yeah, sorry. This should be right. I equals to 1 to m and this is j equals to 1 to okay, so now if I consider the matrix A which have a size of m cross n size. Okay. So the size of this matrix is m cross n. Then the row vector, if I consider and x to be the matrix of size n cross 1, then I can write axi is equals to summation of j equals to 1 to m yes, j equals to 1 to n 1 to n a ij xj, right? Okay, so now And we already know that n is greater than m, right? So for n is greater than m, we know a theorem. Previously, we proved that theorem that if n, so m is less than n, and then so then the homogeneous equation ax equal to 0 has a non-trivial solution, right? So since this ax equal to 0 has a non-trivial solution, that means for this part, for this xj, this n cross 1 matrix, this doesn't have to be equal to 0, right? So if I set x1 v1 plus x2 v2 plus xn vn equal to 0, that means 0 vector, then the summation I equals to 1 to m j equals to 1 to n aij xj with ui vector, this is also equal to 0. Yeah, that means, yeah, 0 vector. That means this, we know that if m is less than n, then this equation has a non-trivial solution. That means for x1 equals to x2 is equals to x3, yeah, so it doesn't have to be equal to 0, right? So they, so actually I don't have to, so that means not every xj is 0, right? And since not every xj is 0, and when I take this summation, this is equal to 0, that means, yeah, so that means this, all these x1 x2 up to xn, all this has yeah, so these x1 x2 xn, this is, all these x's are not 0, but they are, the linear combination of these is equals to 0. So if the linear combination of these equal to 0, that means this set S prime I started with, this is a linearly dependent set, right? Isn't it? Yeah. So okay, that is the proof of this theorem. Okay, thank you very much. That's all for today. Yeah.
Couldn't pick up the part when you changed INGs.